In this lesson, we'll try to look at the basic rotation concepts. The question of rotation comes into picture because we are attaching a frame to the end effector, and we need to keep track of that as the joints keep moving. We need to keep track of the position, location of the origin of the frame, and also the orientation. So we're basically keeping track of how the object that is being handled by the robot is moving. Well, towards that, we need to understand two things. One is two frames uh, that are rotated with respect to each other, and also translated. That is, origin has been shifted from one position to the other. How they can be related? Well, in this respect, we'll start with rotation of frames with a common origin. Origin being the same. For example, now we take two frames, x0, y0, z0 is one frame written in blue color, and another, suppose the same frame is now rotated in so many ways to come to this position, x1, y1, z1. x1, y1, z1 is the frame that you obtain after rotations. How to relate these two frames? Well, for that what we do is take a vector OP, we call it as OP0 when we refer to frame 0, and OP1 when we refer to frame 1. The same OP can be written if I, J, K being the direction cosines with 0 subscripts in frame 0 and subscript 1 in frame 1. The same vector OP can be written as OP0 is x0, I0 plus y0, j0 plus z0, k0 in frame 0, and similarly with respect to frame 1 we write it as x1 I1 plus y1 j1, etc., where I, j, k are the unit vectors along this axis. Okay, now if you look at the x component with reference to of this vector OP with reference to frame 0, it can be written as OP0 dot I0 as a dot product. It can also be written as OP in terms of, it's also OP and OP1 being the same. The dot product of I0 with OP1 is also the same, x0. So we can write it as OP1 dot I0, which will result in x1 I1 dot I0 plus y1 j1 dot I0 plus z1 k1 dot I0, where we replace OP1 by this. So similarly, we can write y0 and z0 also as the dot products of OP1 with j0 and k0. Well, these three equations together can be written in the matrix form in this fashion, where we are relating x1, y1, z1, the coordinates of a point P expressed in frame 1 to that expressed in frame 0. This is called the rotation matrix. Well, as you see, the first column of this matrix happens to be nothing but the direction cosines of I1, rather that's a unit vector along x1 along x0, y0, z0. Similarly, the second column is nothing but the direction cosines of a unit vector, components of a unit vector along y1 uh, with respect to x0, y0, and z0. That is I0, J0, K0, and so on. Similarly for vector K1. So this thing we write it as P0 is equal to R10 P1. R10 is that rotation matrix that relates frames 1 and 0. So R10 is a matrix that relates rotation matrix that maps a point in frame 1 to frame 2 coordinates in frame 0. Okay. If you take two frames like this, we'll talk about basic rotations. Basic rotations are those if you obtain one frame from the other by a rotation about one axis only, then whatever that relation between the two frames is called a basic rotation. or a basic rotation matrix? Well, suppose you move about z by an angle theta, then you know x0 and y0 would have moved to x1 and y1 like this, let us say. Now what is the relation between the two? Well, from whatever we have seen earlier, the direction cosines of x1 along x0, y0, z0 happen to be first column. Well, this is theta cos theta, and this one along y0 is 90 minus theta cos is sin theta, and it has no component along z1. So you will find the first column is cos theta sin theta 0. Second column is direction cosines of y1 along x0, y0, z0. Y1 along x0 is cos 90 plus theta, which is minus sin theta, and its component along y0 is only theta part, cos theta. So, and along z it has no components. And the third one, z1 is totally purely along z0, no components along x0 and y0, so it is 0, 0, 1. Therefore, this is the basic rotation matrix about z, and that is R10, that is 0. The initial matrix is now rotated about z by theta. That is a new frame 1 that you got, that is related by this matrix, and we call that as RZ theta. Basic rotation about z by an angle theta is given as RZ theta. Well, if you have two frames like this, you want to know what is the rotation matrix, matrix that relates these two. Well, applying the same definition, x1, that is only difference is, x1 is along z0. Okay, x1 is along z0, and no components along x0, y0. Therefore, it is 0, 0, 1. And y1 is totally along this. So, only along y0 it will have full component, no components along x0 or z0. So, 0, 1, 0. Similarly, z1 is along the negative direction of x0, no components along these two. Therefore, it is minus 1, 0, 0. So, readily by inspection also, well, if the clear enough, you can write a rotation matrix by inspection also. Well, when we come to to translate so the same two frames that we had earlier slide. Suppose there is a point P which is 3, 4, 6. You want to relate it to. You want to find out what are the coordinates of this point with respect to frame 0. Well, simple, that rotation matrix multiplied by 3, 4, 0. That will give you minus 6, 4, and 3. Well, it makes sense because 3, 4, 6 in this frame, x0, rather x1, y1, z1, 3 along x1 is along z0. Therefore, when it has to be 3 in the z location, and z is 6. It is minus x0 direction. So in the x position, it goes to minus 6. So coordinates of this point can be readily seen to be minus 6, 4, 3 because the two frames are simple enough, and the axes are parallel in the way. In such cases, you can readily write in. And suppose you have a rotation of 30 degrees, or what is RZ theta? Cos 30 minus sin 30 minus sin 30 cos 30 is 0, which is root 3 by 2. So you can readily write the numbers like this. Yeah, coming back to one more thing. Suppose I had minus 6, 4, 3 in frame 1, and I want to know them what they are in frame 0. Well, then it will have to be, the conversion will have to be P1 is equal to R01 instead of R10 P0. Okay, that R10 happens to be the notation of 1 with respect to 0. It is nothing but R10 transpose. It also happens that R transpose is also equivalent to the inverse of this matrix, and because it happens to be this basic rotation matrices happen to be orthogonal matrices, the transpose is also equivalent to the inwards. Okay. So, and other than this, the other two frames that we have, basic rotations, other two basic rotations are about y, your x0 will go to x1, z0 will go to z1, and this is the new frame with the basic rotation. And when you look at this, by inspection also you should be able to, because y happens to be the same as before in the frame 0 and 1, it will have 1 in this position. And other things by inspection can be written as cos theta minus sin theta, cos theta, sin theta 0, cos theta in the first and third columns. Similarly, rotation about basic rotation about x-axis around this. Well, this is the new frame, x being the same as x1 being the same as x0. That's why you get the first column as 1 0 0, and second and third columns you can find by inspection that these two. You may check it for yourselves. Okay. Okay. So these are they called the basic rotations. Then we'll look at composition of rotations. You got one frame like this, is rotated to frame position O1, is further rotated to frame position to another position O2. Then how do we relate a point in frame 2 to point to that in frame 0? Well, it is done by composition. We know a point in P1 can be related as R10, P1 is P0. Similarly, you can relate these two frames as P2, P1 is equal to R21, P2. Okay. So in the place of this P1, you substitute this, and then you will get P0 is equal to R10 into R21, P2. Well, there's a relation between this frame and this frame directly. Frame 2 to frame 0, we can directly write it as R20. And that R20 happens to be equal to R10 multiplied by R21. We sort of post multiply because we are rotating about the current frames. We are rotated about to this, and then this R21 rotation I talked about as rotation about Z1. Z1 is the new Z0. When it transformed after this transformation, it came to this position. This is the current Z position. So this current position, because the rotations are about the current positions, they are getting post multiplied. If on the other hand, if the multiplication, if the rotations were to be about a fixed axis, suppose this is the original axis, the first rotation was about, let us say, y, and it came to this position. Next rotation I don't make about the current z. I want a next rotation I want to make about z, but not about current z. I will make about this z, which is not parallel to probably any of these axes. Then this rotation that I make, or z theta that I make, will have to pre-multiply. So in that case, it will be R21 into R10. So you got to be careful whether you are rotating about current frames or fixed frames. If you are doing rotating about current frames, you post multiply each of these rotations. If you are rotating about fixed frame, each further rotation that you make, you have to pre-multiply the previous rotation matrices. Well, we'll look at the translation in the next lesson.